In today's lesson, we're going to continue looking at the linear regression model, and in particular, we're going to think about how we can go about actually estimating the model parameters. So, specifically, what we want to do today is both understand what the best linear regression line is going to be and how we would solve for that mathematically. We want to understand how we're going to interpret the different regression coefficients and understand the limitations with this. We also want to see what we would call the variance breakdown, and so understand sort of where the components of variance are in this model and what these different components sort of mean. Finally, we'll look at what's called the coefficient of determination, and we'll see some of its limitations. The coefficient of determination is a measure that some people like to use to describe how well a linear regression fits. I don't personally like it very much, and so I'll talk about some of the reasons why I'm not the biggest fan of it, but I think it's important to see because it comes up sort of all around. So, to motivate the lesson today, I want to begin by pointing out that we all actually understand how we would draw the best regression line, right? So if I give you some data here, you can see it's plotted on the XY axis or scatter plot. And if I were to ask you to draw the best line through these data that you could, I think we'd all agree on which line this is, right? So it's not going to be any of the lines that go with a negative slope, right? It's obviously positively sloping. And there's no point drawing a line that's going to sort of miss large chunks of the data, even if it sort of crosses through the middle of it correctly, right? And so we're all going to wind up on one of these lines that approximately goes through the data. It might be slightly off if we're doing it by hand or if we're eyeballing it, but we all sort of agree that the line is going to be the best line if it passes through as much of the data as it can, if they're sort of, equally dividing the data above and below the line, all of these types of things. Because we're all going to agree on this intuitively, it's kind of nice to know that the math that we're about to look at, the procedure for actually estimating that line, is just capturing this intuition and sort of allowing us to formalize it. Okay, so how do we actually do that? Well, we want the best possible line, right? And what we know is that that best line is going to be defined by both the intercept and by the slope, right? So if we think about trying to determine some estimators for that line, so we'll say beta 0 hat and beta 1 hat, then what that's going to give us is some estimated point, right? And if you think about it, we're sort of estimating the mean of this point, right? So in the last lecture, we saw that the expected value of y given that x is equal to x is going to be equal to beta 0 plus beta 1 times x, right? And so then if we wanted to estimate the y, assuming that we had some observed value of x, well then one of the ways that we would like to do this is by estimating the mean, right? And so then we could come up with some estimated value of y. It's going to be based on the estimated value of our intercept, the estimated value of our slope, and our observed value of x. And so right here is going to be an estimation, right? And we know, or we've said, that the true y is actually going to be beta 0 plus beta 1x plus epsilon, right? Where this epsilon is our noise term. And so if you were to think about if we got our estimators exactly correct and we took y minus y hat, right? So if we subtract this, then what we're going to end up with is just epsilon, right? Now, of course, beta 0 hat and beta 1 hat aren't going to exactly equal the quantity that we care about. And so instead, we can sort of think about estimating epsilon using what we'll refer to as a residual. And so we'll define EI to be equal to yi minus yi hat. And the idea is that this residual sort of estimates this error here. In other words, the residual is estimating how far our estimated line is from the true observed value. Right? And so we call these values residuals. And the idea is that our best line is going to have the smallest residuals that we can have, right? Sort of intuitively, if we think about yi hat are the points along our line, then we want to make the residuals small. But we're going to have a problem. And the problem is that EI is either going to be a positive or a negative value, right? And the issue is that this is going to, if we were to just try to minimize the, say, sum of residuals, this is going to allow us to have really large residuals, even if we don't sort of have to, because the large residuals are going to be able to cancel with negative large residuals, right? So because of that, just minimizing the residuals sort of isn't enough. And instead what we're going to do is we're going to look at the squared residuals. So we're going to take this sum from I equals 1 to n of yi minus yi hat squared. And we're going to try to minimize this. And in particular, we're going to minimize this with respect to beta 0 hat and beta 1 hat, right? And if you think back to your calculus class, the way that we typically go about trying to minimize these types of things is by taking derivatives and setting those equal to 0, right? So what I'll do is I'll define L here, and L is the commonly used letter. In this case, it stands for a loss function, and it's going to be a function of beta 0, it's going to be a function of beta 1, and it's given by the sum from I equals 1 to n of yi minus beta 0 hat xi, or sorry, should not have an xi multiplying the intercept, minus beta 0 hat minus beta 1 hat times by xi, we square the whole thing. And then the idea is that we could take the derivative with respect to beta 0 of L, beta 0 hat, beta 1 hat, and we can take the derivative with respect to the slope. And if we set both of these derivatives equal to 0 simultaneously, so set that equal to 0, set this equal to 0, then solving this system of equations here is going to result in equations that we can solve for to get the estimates for beta hat 0, beta 1 0 that minimize the squared residuals, right? And so if we actually do that, we can write down what the form of these estimators is going to be. And we see that we define beta 0 hat in reference to beta 1 hat, right? So we take the mean y bar minus beta 1 hat times x bar. And beta 1 hat is going to be given by this sort of ratio of summations here, where the top summation, we're taking what looks to be a little bit like a covariance term, if you remember that, but sort of the sum of these cross terms divided by the sum of the squared x's, or squared deviations of the x's, right? And so this is going to be how we actually estimate in the simple linear regression case. Now, recall that beta 0 is going to be the intercept for the regression line. And so if we want to start trying to interpret what this means, well, the intercept, or the y-intercept specifically, is going to be the value that our outcome takes on if we set x equal to 0, right? So if we think about the case where we know y is equal to beta 0 plus beta 1 x plus epsilon, right? If we take x equals 0, then we'd have y equals beta 0 plus epsilon, right? And we know that the expected value of epsilon is equal to 0. And so the intercept is going to refer to the expected value of y, assuming that x is 0, right? So beta hat 0 is going to be our best guess we have at the intercept. And then if x is equal to 0, this is the expectation of y, right? And so beta hat 0 is going to be given by the our best guess at the expected value of y, given x equals 0. Now, if x equals 0 has a substantive meaning, right? If that's something that we could actually observe in the real world, the intercept is going to have a meaning. Generally speaking, we might not actually care about x equals 0, right? And if we don't actually care about x equals 0, then there's no real way to interpret the intercept, right? At least no meaningful way to interpret the intercept. Now, recall that beta 1 is going to be the slope of the line, right? And so then beta hat 1 is going to be the best guess we have at the slope of the line. And if we want to try to think about how we're going to interpret the slope of the line, right? Well, let's think about two different values here. Let's say that we have beta 0 plus beta 1 x plus epsilon, right? And then if we think about a second option where instead of x, what we observe is actually beta 1 x plus 1. So we have x with one extra unit added on, and then plus epsilon. And if we take the expected value of both of these quantities, right, we get rid of the epsilons because they have expected value 0. And if we take the difference between these two values here, what we'll find is that the beta zeros are going to cancel out. We'll have a beta 1x in each of these, right? And so those will cancel out, and we'll just be left with beta 1 times 1. And so that's if we subtract up like this. So that's going to equal beta 1. And so the idea with the slope is that the slope is going to be interpreted as the expected change in our outcome if we increase x by a value of 1. Right? So for a 1 unit increase in x, we expect that y is going to change by our estimated slope coefficient. Right? And so beta 1 is actually capturing the relationship between y and x. How does y change as we change x? And of course, you could think about, instead of changing x by 1, if you plugged in a different value here, then you're going to end up with some value times by the slope, right? And so you could sort of scale this all up or down as it makes sense. Now, we need to be careful about two different properties here, or two different concerns here. The ideas are both extrapolation and bad model fits, right? We're going to observe x data over some range. And when we fit our model is going to be fit on that range. You have to be really cautious about extrapolating out beyond that range of x values, right? So if you observe x's between 0 and 100, you have to be cautious about, say, plugging in a value of 150 for x, right? And the reason is we don't know what's going to be happening to the outcome out there. There might be good reason to expect that the same pattern is going to continue to hold. And if that's the case, you can do this, right? But it's also possible that outside of the range that you've observed, a very different pattern emerges. And if that's the case, then our linear regression model is not going to hold outside of that range, right? And so really, when we start trying to interpret these values, or we start trying to make predictions, we have to be mindful of what was the data that we were actually looking at, and trying not to draw conclusions beyond the sort of frame of reference that we have within our data. The other thing that I'll point out is that not every linear regression is going to fit well. We saw when we were looking at those scatter plots, there are oftentimes going to be relationships that are not linear between these variables. And if we fit a linear regression there, we're going to be able to get estimates for our slope and our intercept, but that doesn't mean that they're going to be a good relationship, right? And if that's the case, then using those estimates is not going to provide us with much utility at all, because it's not a good relationship for it. Right? So we have to be careful about not drawing conclusions that are beyond the scope of the data. And we also have to be careful to make sure that the linear regression is actually the appropriate tool to use. So with sort of the how we fit it and the interpretations out of the way, we can start thinking about the sources of variance in the model. So if we actually look at the squared residuals, the sum of the squared residuals, this actually gets a common name in regression analysis, and we call it the error sums of squares. So it's the errors that we're making with our regression model, and we square them, so it's the sums of squared errors, right? SSE, sum of squared errors, people call it the error sum of squares, okay? This is how much variation there exists in our outcome, so how much variation there's left in y, that did not get captured by the model. Right? It's how many mistakes is the model making? How much variance is there around the best line that we can predict? We can estimate our variance as the sum of squared errors divided by n minus 2. Right? And if you think about what we were looking at when we looked at sort of that derivation, well, we saw that EIs are sort of estimating those epsilons, right? And so this makes a little bit of sense. We're dividing by n minus 2 in this case because we've actually estimated two parameters. So it's this idea of degrees of freedom. We were dividing by n minus 1 in the previous case because we just needed the mean. Now we need two parameters, right? We can also think about the total variation of y, right? Which is something we've looked at before. It's just going to be sort of the variance of y. But if we don't scale it down, then we could have the sum of squares total, right? And this is how much variation there is in our outcome in total, right? And so if we had used the mean to estimate it instead, we can just do yi minus the mean all squared, sum that up, right? And so we've seen this quantity before, and that's sort of the full variation that's in our value of y. And so what we have is that the sum of squared errors is going to be less than or equal to the total sums of squares. And one way you could see that is because if we wanted to, we could just actually plug in beta 0 equals y bar, beta 1 equals 0, and then that's going to give us exactly this, right? And so we can always do at least this good. Most of the time we can do substantially better, right? So we have our sum of squared errors is going to be less than or equal to the total sums of squares. If we actually take the difference between SST and SSE, that's how much variation is captured by the model. That's how much of the variance in our outcome is actually going to be explained by the linear regression model that we fit. We call that the regression sums of squares. It's called SSR, right? And so essentially what we have here is we have sort of three sources of variation. We can think about the total sums of squares, SST, is going to be given by this error sums of squares, which is what's not captured by the model, plus the sums of squared from regression, which is. So this is missed by the model, and this is what's captured by the model, right? And so the idea is essentially the more variation in our outcome we can capture with our model, the better that our model is doing at explaining the outcome, right? So if SSE is really high, so if we have this is much higher than what we capture, then our model's not doing great at capturing much of the variation in our outcome. If we actually have that the sums of squared errors is small compared to how much we're actually capturing, then we're capturing a good deal of the variation, and the model seems to be fitting well. At least that's the theory. So one way that we can actually think about this is using what's called the coefficient of determination. And so the coefficient of determination is given by SSR divided by SST. Or you might see this equivalently as 1 minus SSE over SST, right? These are exactly the same thing. And the idea here is that this is going to be a fraction which corresponds to what percentage of the variation in our outcome can we explain with the model. So it gets the symbol r squared. It's called the coefficient of determination. Lots of people will just call it the r squared value. And the r squared value is interpreted as the proportion of variance in y that's captured by the model, or that's explained by the model. So it's typically used to indicate the strength of the relationship. It's going to vary between 0, which would mean none of the variance is explained by the relationship, up to 1, which would be all of the variance is explained by the relationship. And this sort of provides people with an indication of how strong is the relationship, right? The higher the r squared value, sort of the better the model is, the more faith people end up putting in the model. It's used all over the place. It's also received a lot of criticism. And my advice would be that when you're fitting regression models and people have not asked you explicitly for an r squared value, don't use it. This is a little bit controversial advice, probably. And the rationale is essentially that the r squared value isn't giving us anything that we couldn't get through other measures, and it's largely a misinterpreted value, right? So we saw when we were looking at estimators in general that we can calculate the mean squared error for different values, right? And so the mean squared error can still be computed here, and that's going to still give us an indication of how good does our model fit the data, right? Part of the problem with our r squared value is it's often talked about as how much of the variation are we explaining with the model, and then we're using that to indicate how good is this model? Did we get the right model, right? And it's that last leap that's going to be problematic, right? It's very possible that you're going to have a linear regression, which is theoretically justified and is the best model that we could come up with the data, that's not going to have a particularly good r squared value, right? And that's because the sum of squared errors, well, that could just be high, right? There could just be a lot of noise in our measurement. And so because of this, sort of this adherence to rules around the R-squared value are not really getting at what they think that they're getting at very often, right? And so R-squared tells us something. It tells us, what's the proportion breakdown of variance, and that's not nothing to know. But from my perspective, the MSE is going to be a better indicator of how well the data is actually fitting. And the R-squared is typically going to lead to more confusion than it clears up. There's also becomes issues with needing to do adjustments to this in sort of more complex regression models. We're not going to be looking at those there. But I guess this is all to say, very briefly, R-squareds are important to know. There's going to be lots of people who ask you for them. It's worth knowing where they're coming from. But for your own sake, I don't think the R-squared is a particularly useful measure, and I probably would not be applying it if you're given the choice. So, in summary, linear regression attempts, the estimates are attempting to find the best possible linear line. We use that through the least squares procedure. It's where we take the squared residuals and we find how to make those as small as we can. We have a closed form for both the slope and for the intercept. The intercept gives what we expect would happen at x equals 0, assuming that's some meaningful value, and the slope captures the expected change in our outcome when we change x by 1. Total variance can be decomposed into the regression and the errors, and we can take the ratios there to get the coefficient of determination, but I would be cautious in applying that. So in the next lesson, which is actually the final lesson for the course, we're going to be looking at how we start to do some inference around these regression models. So I hope to see you all in that lesson.